that ENSUS Discussions is one of the many actions that the chair initiated since its inauguration in March last year. ENSUS stands otherwise for energy sustainability and has been established jointly by OCP Group and UM6P with the aim to help bring understanding, address challenges, and identify opportunities related to different trust subjects that we have identified, such as energy storage, conversion, CO2 capture, water energy mixes, etc. So today, we welcome Professor Giraud, who accepted our invitation to be speaker at this edition. Thank you for that. I also welcome Dr. Debajit Bora, who is an assistant professor at the MSN Department, Materials Science and Nano-engineering Department, working on hydrogen systems, and Fouad Ramous, Professor Associate Professor at MSN, working on diverse subjects, planning on storage and conversion. They will both be members of a panel that will, after the presentation, Professor Giraud will discuss with him different questions related to the subject. So let's go to our guest, Professor Giraud. I'd like to introduce him. He's the director of H2 Valais. For the last 30 years, Professor Giraud has had managerial responsibilities for chemistry and electrochemical engineering at EPFL, Switzerland. He was twice the chairman of the Department of Chemistry, now called the Institute of Chemical Engineering Sciences, twice the head of the Chemistry Teaching Commission in charge of Chemistry and Chemical Engineering Education, EPFL, now called Section of Chemistry and Chemical Engineering. He was also director of the doctoral program in chemistry for the period 1990 to 2000. He served as the Dean of Bachelor and Master Studies at the EPFL and has supervised a comprehensive teaching reform with the definition of a new curricula starting in September 2013. These changes included the introduction of new first-year curricula with 2/3 of common courses for all scientists and engineering sections, and of a new bachelor curriculum integrating more closely lecture courses, exercises, and practical modules. He was involved in major overhaul of the master programs and has introduced or has led the introduction of MOOCs for specific courses. So I'm sure many of you recognize many of the terms here, and I do state them because in discussing with Professor Giraud, it feels sometimes that he should be with us here at the university. Professor Giraud is also the recipient of many awards. So he has a Faraday Medal of the Royal Society of Chemistry, a Fellow Award of the American Society of Electrochemical Chemistry. He's also Fellow of the Royal Society of Chemistry in the UK, among other things. And today, he will talk to us about hydrogen Gigaprojects and mobility applications. So the floor is yours. Thank you.
So first of all, thank you very much, Professor Vanadhy, for the invitation. And thank you to your colleagues also for the kind welcome. It's a pleasure to be there on this beautiful campus. It's really impressive when you visit this campus for the first time. Now you are all used to it, but coming for the first time is beautiful. Anyway, the talk of today is about hydrogen Gigaprojects and mobility application, because if you read the news, you will see that everybody speaks about Giga hydrogen project. So as Professor Lamy said, I come from EPFL. Just for those who don't know where we are on the Johnny Valais opposite Evian. Anyway, So if we look at, for example, some press announcement last year, for example, Shell in summer of 2021 was announcing 100 megawatt of hydrogen. And last summer, 100 megawatt looks like a big project. But if we look at now the press release of today, all the press releases are on the gigawatt scale. If I take, for example, this ideal ambition project from Spain, you can see we speak about 67 gigawatt of electricity capacity. It's enormous. I don't know how much is the production of Morocco, but I guess around 28 gigawatt, sorry. So it's twice the Moroccan electricity production going into hydrogen. If we look at the Swiss company H2 Energy, they signed an agreement with Plug Power of the US, also for a gigawatt scale electrolyzer, and this one is with offshore wind. If we go to Saudi Arabia, they speak about the world's first gigawatt scale hydrogen electrolyzer with ThyssenKrupp. ThyssenKrupp is known for doing chlorine electrolyzer, but we are speaking here about 500 billion. That's a lot of money. And of course, the Americans have to have the biggest, because the Americans always have the biggest. So they have the world's largest green hydrogen project with Canada for 5 gigawatt, and so on and so on. And if I look at just 2 weeks ago, Total Energy of France signed an agreement with Adani of India for 5 billion investment to take 25% of Adani to do hydrogen production in India, and we are speaking of about 30 gigawatt. So again, we are really the big number scale, okay? So just to speak about Morocco, the only thing I could find was this announcement by Total that Total will invest in a mega project. So this one is not giga, but it's a mega project in Guelmim, which I believe is south of here. Is that correct? Yes. So you know all about that? You know more than me about it? Anyway, so why all those announcements? Is that just because the planet is really having a transition? Now, if we look back, the 19th century has been powered by coal and steam engines. So we all know that. The 20th century has been powered by oil and combustion engine, and electricity was a vector of energy. And of course, in 2022, the question will be, what will be the energy of this century? And of course, if we believe in global warming and so on, we think it will be powered by renewable energies with massive electrification and massive use of artificial intelligence. And then the question is, can hydrogen be a vector of energy for this new economy? That's the key question. Now, if I take the EU roadmap, the EU is really pushing for a large-scale generation of renewable energy, and that means mainly for Northern Europe of wind, for Southern Europe of sun. Then the idea, of course, is to distribute this energy across Europe for the different sectors and regions. Can we use the storage as a buffer? That's a good question. And basically, what are the goals? Goal number one is to decarbonize transportation, and mainly, I guess, heavy goods transport. Decarbonize heating and power for buildings. You can now buy a water heater based on hydrogen. And of course, decarbonize industry use. And in this one, green steel is really on the agenda. And I guess that Maghreb Steel in Morocco is has ideas of doing. I say, I don't know that. Okay, so Maghreb Steel, I guess, has also ideas on how to decarbonize steel production. And of course, at the end of the day, it will also be as a feedstock. And that's what Power2X, the conference in Marrakesh today, is all about. Can hydrogen be used as a feedstock? So basically, this is the roadmap. And being a professor of chemistry, let's speak about chemistry and not too much about politics. And let's start with the colors of hydrogen. So the hydrogen, as we know it today, 95% of the production is gray hydrogen. So at the beginning of the 20th century, hydrogen was produced mainly by gasification of coal, and that's what we used to call town gas. London, Paris were littered with gas lights, and this gas light contained hydrogen, methane, a mixture of everything coming from coal, and that was the beginning of the 20th century. Actually, in 1801, Philippe Le Bon in Paris, during Napoleon's time, had a house where he was producing hydrogen in his cellar to lit the building. So if you go to Ile-Saint-Louis in Paris, go and visit Louis Le Bon's house. Anyway, when the petrochemistry came, people started to stop gasification, and they started to go for steam reforming of methane, or even autothermal reforming of methane. The idea there was to react methane with water to do CO and hydrogen, so what's called syngas. And if we use the reversible gas shift reaction, reacting carbon monoxide with water, we could produce hydrogen and CO2. And this is why this hydrogen is called grey hydrogen, because when we do steam reforming, we produce hydrogen and CO2. Now, if you can capture CO2, the hydrogen becomes blue by energy, because it is assumed that you have no CO2 emission. So this is neutral production. What people call green hydrogen is done by electrolysis. That will be mainly the talk today, because I'm an electrochemist, where you split water into hydrogen and oxygen. And there is another type of hydrogen I want to speak about today, is turquoise hydrogen made by pyrolysis. As a physical chemist, I think this topic has been understudied, and I believe that pyrolysis is a major route for the future, where basically you take CH4, you heat it up to pyrolyze it, and you end up with carbon solid that you can store or put on the ground, and hydrogen. And this one is really negative carbon capture, because out of the methane you get solid carbon that you can put in the field as biochar, or that you can simply store as your own. So in my laboratory, we've been playing with indirect water electrolysis. I will say a few words about Redox battery, that's for the students. And I will say a little bit about waste pyrolysis, because I am a great believer in circular economy, and I think the academic group that we are should really work hard to develop circular economy for this planet, especially for the young people. Anyway, so why hydrogen is a vector? Because if we go for renewable electricity, of course, we cannot transport electricity over too long distance. You can have a power line maybe up to 1,000 kilometers, but if you want to export, let's say, electricity, solar electricity to the UK, you would need a special DC power line, which will cost a fortune, and there are plans about it, but it's not yet made. And of course, if you want to do renewable electricity, you should do it better in countries where you have sun, like Morocco, than in Switzerland, where you have wind, like in Morocco, rather than Switzerland, where we have no wind at all. And therefore, what's called the capacity factor of Morocco is one of the greatest for this region, because for a given capex investment, that's where the country where it will produce the more kilowatt hour. So once you've done your green hydrogen, the question is, what do you do with it? And of course, you can transport it by pipeline, or you can liquefy it, or you can export it. But best, you can use it for your own use, for example, to do ammonia and fertilizer. Now, other people now, when they speak about green hydrogen, that's the Swiss and the German approach, is to say, okay, at the moment we use methane, we are going to do steam reforming, then we do blue hydrogen. We can sequester, we can capture the CO2, let's say, in Germany, and in this way we have blue hydrogen. But other people say, no, what we could do is to transport the CO2 back by boat to where the methane came from. And if you mix it with green hydrogen, you can do a methanation reaction, like the Sabatier reaction. And then you end up with green methane. Your methane suddenly becomes green because it's artificial made with hydrogen. You can transport it, and basically the green hydrogen can be used, let's say, in Europe. And now it's for you to believe if it's a good business or not. at the moment, the methanation reaction has a yield which is not that great. So if you look, for example, from renewable electricity to green hydrogen, you lose 30 to 40%. Let's not forget that electrolysis has a yield of 60%. So if you go to the bottom, what I would call a Swiss German route there of methane, you lose 60% to do the green hydrogen, and then you use another 30% to do the methanation. At the end of the day, it's a very expensive cycle. But some people are really investing money into that. And of course, you are not obliged to transport the CO2. Let's say that we make CO2 in Switzerland. What, for example, Morocco could do is to capture CO2 from the air and charge the Swiss for the CO2 that they will inject in the ground while the Swiss export it into the air. And afterwards, the only thing they need to do is to transfer money, and it's easier to transfer money than to transfer CO2. You would agree with that? So, and the Swiss like to transfer money anyway. So I believe direct air capture has a lot of future. And since I'm an electrochemist, I would like to propose a mechanism. So we all know air capture from amines through caustic solution, alkaline solution, through different type of routes. But there is one electrochemical route that is used for air capture. Do you know an electrochemical route for CO2? Who knows one? No? So I have the pleasure to work for the company Verdox in the US, which is a MIT spin-off. And the concept here is easy. You have one electrode, but with anthraquinone polymer. You have a membrane, okay, just a separator, and another layer of polymer made with ferrocene. When you apply a voltage, you reduce the quinone to the radical anion, and for one electron, you will capture 1 molecule of CO2. On the other side, you oxidize your ferrocene to ferricinium. And then when you reverse the polarity, you release the CO2, and this CO2 battery gets discharged, and the CO2 is released. The advantage that you release clean CO2 that you can use for Fischer-Tropsch reaction if you want to, methanation reaction if you want to. And the idea of that is that because you need electricity, if you have efficient renewable energy like in Morocco, you can do direct capture also by electrochemistry, the same way that you would do green hydrogen by electrochemistry. And so I've seen prototype of that in the US, and they have plans for kiloton, if not megaton CO2 plants in the US. This company was financed by the Bill Gates Foundation. They got more than 80 million to develop their system, and they are quite efficient. And if I don't want you to look at all this table, but just the number there, you need less than 1 megawatt hour per ton of CO2. So at the moment, how much is the price of CO2 in Europe? About 50 to 70 euro. Okay, so if you can make cheap electricity, and let's say your megawatt hour by cheap electricity is around 20 to 30 euros, you can make a lot of money by pumping CO2 from the air, putting on the ground, and sell the Germans or the Swiss certificate for CO2 capture. And I guess that's a big money, and it's quite easy to store CO2 on the ground in Morocco because you've got salt domes and you've got very nice geological structure to store CO2 on the ground. So CO2 could become a big country for CO2 storage afterwards. And so if you compare those with amine or with strong base, you see that electrochemistry for once is very competitive. And again, in Switzerland, we have a company called Climeworks, where they pump CO2 from the atmosphere to inject in Iceland under the volcanoes. But I believe an electrochemical system in Morocco would make a lot of sense. Anyway, I close my CO2 capture bracket. I just wanted to make you aware that there are electrochemical ways to store CO2 in a very efficient and a very clean manner. Okay? It's not a big factory to do that. Okay, so let's go back to electrolysis. Electrolysis is quite an energy-consuming process. The delta G of the reaction is at least 40 kilowatt-hour per kilos of hydrogen produced. The cell voltage is 1.23 volt. And this reaction, of course, is as old as electrochemistry from the 19th century. Here you've got two Leclanché battery electrolyzing water. On the left, you've got hydrogen being produced. The volume, of course, is twice that of oxygen being produced. A very old reaction. I don't want to say too much about the production or the reaction mechanism of hydrogen and oxygen. I know that Debajit has a big plan to study all the electrocatalysis aspect and the mechanistic aspect of hydrogen evolution. What I just would like to say in one slide, we should never forget it's a three-phasic reaction. The metal brings the electron, the solution brings the ions, and the bubble takes away the gas. And that's what I call ménage à trois. And like all ménage à trois, they are complicated, okay? Because there is always one who is going to be slower than the other two, okay? So sometimes the bubble blocks, the ions cannot arrive. Sometimes the ions react, they don't arrive, and so on and so on. So basically, the complexity of gas evolving reaction is at the fact that you've got an electronic conductor, an ionic conductor, and a gas carrier. Of course, oxygen evolution is 4 electrons, so it needs 4 steps. So it's much slower than hydrogen evolution, which is only 2 steps. Okay? And often in an electrolyzer, the cathode where you do the hydrogen is waiting for the oxygen to evolve itself. Okay, because the current should be continuous. So if you have electrons going in one side, electrons should go out on the other side, and they have to go at the same speed. So hydrogen is often waiting for oxygen to happen. Okay. About alkaline electrolysis, it's a very mature process. Okay, in 1922, people in Geneva, Switzerland, patented, for example, this electrolyzer, which has been at the basis of water electrolysis for nearly a century. And in the 1950s, for example, in Norway, where there had a lot of hydroelectricity, people were producing hydrogen on big scale. And even at the beginning of the 20th century, Switzerland was a major producer of hydrogen in Europe simply because we had hydroelectricity, as simple as that. Okay? But of course, afterwards, the oil era came, oil was cheap, and it was much cheaper to do hydrogen through natural gas and oil than through electricity. And therefore, electrolysis started to go down and SMR started to become. Now, how does an alkaline electrolysis cell works? Okay, at the beginning, what you need is an alkaline solution. For example, 25% KOH. Then you need to bring electrons, so you need a cathode. You need to take out the electrons, you need an anode. So at the cathode, of course, you are going to reduce your water to hydrogen. At the anode, you are going to oxidize the hydroxide to oxygen. That's the slow reaction. In the middle here, you need a diaphragm to avoid mixing. In the old days, people used asbestos, but of course, nowadays it's zircon and other polymer type membrane. You need to pass a current from the anode to the cathode. So we should never forget that in an electrochemical cell, of course, the electrons are carried by the wires and by the metal, and in solution, the current are carried by ions. And because ions move by friction in a solution, there is a resistance, and that's where the system starts to get warm. And of course, in order to transfer electron to ion, you need an electrode reaction. So if we look at the distribution of potential in an alkaline electrolysis cell, you see that we have a potential drop at the cathode where we do hydrogen. We have a potential drop in solution due to the migration of the ions. And then we have a larger potential drop at the anode where we do the oxygen. So this is textbook electrolysis for more than 1 century. Okay. Now, to avoid the resistance in the membrane, people started to basically put some grid directly on the membrane in such a way to bypass the omiclos in solution, and that's what you call the zero gap cells. They operate usually at 80 degrees. They have an energy loss of 30%. The cell voltage should be less than 2 volts to be useful. The current yield is very good, 98%, and the current density is not bad, 6% minus 3, depending on the manufacturer, kiloohms per meter square. So it's a big current that we are passing here. we enter, of course, KOH in the solution. We end up with H2 and O2. Now, when you see a diagram like that, you would think that you've got liquid in between the electrons. No, what you get is what I would call a chantilly cream type electrolyte, because it's bubbling so much that in fact you electrolyze foam. Okay? So if we were to put a camera in the electrolyzer, you would see a chantilly cake, basically, not a liquid. Okay? But if you want to do more hydrogen, you put them in series, and this anode in the cathode in the middle end up at what's called a bipolar plate. Now, if you want the current has to be constant through the system. So if one cell is not too performant, the other one has to wait for the slow one to go to. Okay. Now, you can stack them up to, let's say, 100 cells in series. So if you have 2 volts, 100 times 2 volts is 200 volts. So that's quite good for power electronics. Up to 1 kilovolt, all the people who do power electronics can easily, you can buy a transformer, rectifier, and so on, up to 1 kilovolt. After 1 kilovolt, power electronics start to be costly. Okay, so that's why usually people start 100. Of course, when you got 100 in series, out of 100, one could go wrong. If one goes wrong out of 100, it slows the full stack. Okay, so what people would do normally, they would shunt the faulty cell if there is really a problem. But something I forgot to say about all those diagrams, we will show parallel plates. Okay, so in the current distribution, if the plates are not ideally parallel, but one, let's say, is a bit like that, all the current will go where the distance is the smallest, which means that you get oil point. If you get oil point, you might burn the membrane. Okay? So there is a lot of engineering in making a stack, and making the things parallel is one of them. Okay? And that's why often people use titanium as a bipolar plate, because you need rigidity. Now, all that is known for 100 years. So what we should teach students about electrolysis? What we should teach them about electrolysis is the balance of plant, how to run such a system. Okay? It looks trivial by drawing. It's not trivial at all as soon as you operate it. Is the voltage fluctuating? Do you have high frequency noise on your voltage? Is your voltage signal clean? And so on and so on. Is the temperature changing too much? Is the pump being blocked and not providing enough KOH? Is the evacuation of the hydrogen doing fine? Okay. So electrochemical engineering is not so much to develop a new electrolyzer, but it's more on how to operate them properly. Okay. Because if you don't operate them properly, they degrade. Okay, like any object that we have, if we don't take care about our car, the car will degrade even faster. Okay, we all know that. Electrolyzer is the same, and those things cost so much money. They are built for 30 years. So if you want your electrolyzer to last 30 years, you better be nice with your electrolyzer and look after it carefully. Okay. So if we look at the balance of plant of an alkaline electrolyzer, as I said, the power electronic transformer, rectifier, nowadays you buy from many companies. The electrolyzer, you've got also many suppliers. Oxygen, usually oxygen is released to the atmosphere because people make so much oxygen they don't know what to do with it. So they just give it to the little birds. Then the light tank, you have to make sure that your KOH is pure, that you don't have any CO2 entering into your KOH, because if not, you do carbonate. If you have carbonate, you block the pipes and blah, blah, blah. So you have to be careful. You have to scrub your hydrogen to make sure there are no oxygen which has been leaking to your hydrogen, because you don't want to have explosion. So you need to scrub. You need then to compress, to deoxidize, remove the oxygen, to dry it, and then to store it. As you can see, in a normal operation, the 40 kilowatt hour per kilos becomes more like 50 and over kilowatt hour per kilos because we have a balance of plant. So an alkaline electrolyzer is what I would call an electrolyzer for chemists, because it's really a chemical factory. Now, we could have a look at the chlorine industry, because if water electrolysis faded away in the second part of the 20th century, chlorine industry continued to develop nicely. And then you can do a very large scale electrolyzer In the case of chlorine, I remind you that on the left you use dilute sodium hydroxide, on the right NaCl. On the right you get therefore Cl2, on the left you get H2. And those companies like, for example, Thyssen Group in Germany, know how to operate those 100 megawatt cell. As you can see, it's quite big. And if you have a pacemaker, if I were you, I would not work in such a factory because the magnetic fields are so strong that you go. So in England, you have companies like Ineos who also can do that very nicely. As you can see here, the current density are about 6 kilograms per meter square. What is interesting to see is the things on the left. Expected lifetime is 30 years. But you see that the anodes where you do the oxygen is the weak point of the system because they have to change around every 10 years. Because when you do oxygen, you oxidize and you destroy your anode. And therefore, the anode is always the weak point of the electrolyzer. Now, since the discovery of perfluorosulfonic acid, of course, there is another type of electrolyzer on the market, which we call the Polymer Electrolyte or PEM Electrolysis cell, where basically is based on a proton conductor. Again, on the right, you will put an anode. So in this case, the anode is simply a graphite felt with some particles, catalytic particles on it. The cathode, again, will be a graphite felt with other particles, platinum on it. The proton will be now the only ions conducting the current. You feed the anode with water, you remove the oxygen, and you get the hydrogen on the left. Again, we are going to put those afterwards in series. So platinum for on the carbon on the left, iridium or ruthenium on titanium on the right. Of course, nowadays, the production of iridium is a problem because most iridiums come from Russia and South Africa. So that could be a source of problem. But anyway, if that was the only problem of the war in Ukraine, that would be fine. But anyway, we have bigger problems than that. Anyway, so what else to say here? That, of course, you need afterwards to structure your electrode to have a flow field where you bring the water, you remove the gases. That's fine. The protons, as we said, goes across the membrane. The gases go on each side. And here you put here a little layer of recombination just to reoxidize any hydrogen that would venture through the PEM membrane, not to make any explosion. Now, again, you stack them. And the beauty of the PEM electrolysis is that basically you have zero balance of plant because it's basically a solid state device. So that's what I would call electrolyzer for physicists. If alkaline electrolysis was electrolyzer for chemists, this one is electrolyzer for physicists because there is basically no chemistry behind it. The only thing you need to do is to separate the hydrogen and the water to dry it and to store it. So the balance of plant is much easier. Now, if you look at a PEM electrolyzer, as you can see, it's very compact. So to conclude, after 1 century of electrolysis, we have 2 good technology to do electrolysis. Okay. So the question is, are we ready to do Gigaprojects? All those Gigaprojects which are announced, can they be made? But to do a Giga electrolyzer, you need Giga production of electrolyzer. You don't have any at the moment. And there are factories called Giga factories to do electrolyzer being built. That will take 2 or 3 years before they arrive. Now, the key question is, if I take a country like Morocco, where would you put your green hydrogen production? Where would you put it?
Next to the coast.
Of course, next to the coast, because the raw material is water. Now, deionized water is not very expensive, so deionizing water is cheap compared to the energy required to do the electrolysis. Of course, you have to worry about heat evacuation. So being by the coast is quite nice because you can use the seawater for cooling your plant. And afterwards, the advantage that if you do it with your own renewable energy, let it be wind or solar, you don't really need to care about a transmission line because you just produce your electricity locally. and therefore you know the price of electricity because it's the price of your capex to do the renewable energy and the capacity factor of your system. Whereas if you do that in Europe, where it depends on the price of electricity from the grid, at the moment this price is going up and down like crazy, and it's impossible to make a business plan to produce hydrogen in Europe. Anyway, and of course you have to store it. And that's where in Morocco you have a big chance, because I'm going to say that the S1, you say? As you said, on the coast from here. Yeah. You've got the salt dome, and basically Morocco is an ideal geology to store hydrogen. So basically you don't have to worry about the storage. Now, if you want to worry about the transport, you can say, okay, I'm going to do a pipeline and I will send it through Gibraltar, but you have to be fluent in the Spanish. Of course, you could transport it, liquefy it, and send it by boat. The French are selling liquid hydrogen to Guyana for the rockets, for the Ariane rocket, and so on. And of course, the best in Morocco is to use it internally, to distribute it within Morocco before to think about exporting it. Because I guess you need it like everybody else. So my advice, serve yourself first and then sell the rest. Anyway, so that is just to give a few orders of magnitude. 1 megawatt of electrolysis produces 100 tons per year, which is not that much. One truck consumes 12 tons per year. So with 1 megawatt, you do 10 trucks. Okay? So that's why people want to go to gigawatt, because then they will do 10,000 trucks. Anyway. When people speak about what will be the price in 2030, I've used this slide from Goldman Sachs, but nowadays, because of the war, the concept of price is totally useless, because all the raw materials go completely crazy, and I think nobody will know what will be the price of electrolyzer even next year, so even less in 2030. So if the world was normal, if the world was like before, people were expecting the price of electrolysis to go down to about $500 US per kilowatt. So that was the projection. Now, what we could see in the projection is that what is it going to be used for? So if we look on the right here, 2050, that's what BP thinks the world will be in 2050. It thinks that first we will do feedstock for other chemicals, maybe ammonia, maybe methanol, maybe synthetic fuel. Industry, that's mainly steel and combustion. Buildings a little bit. Direct transport, which means fuel cell trucks, is a little bit. But hydrogen-derived fuel, and that is ammonia, I guess, mainly, will be a big chunk. Power burning directly hydrogen, and others, I don't know what they mean by others. So if I look at hydrogen with the eyes of a Swiss, in Switzerland, we have no electricity. If you take any newspaper at the moment about Switzerland, they say we will have a penury of electricity next winter. Buy candles, okay? Because we will be short of electricity. The Germans will be short of electricity. The French will be short of electricity. And since we buy our electricity from the French and the German, the chance that we will be short too is quite big. Yeah. So if we have no electricity, even for doing cooking, we're not going to do hydrogen. So in a country like Switzerland, where can we get our hydrogen from? Before the war, we thought that the Russians would sell us some blue hydrogen, because Gazprom had the ideas of doing pyrolysis in Russia, mixing the gas hydrogen with the natural gas and exporting to Europe. I think this route now we can forget at least for a while. Of course, in the North Sea, there are many people who have plans to do electrolysis directly using offshore wind energy. And of course, we have the route from the summer. So Switzerland has no renewable energy as such. We have very little sun and no wind. So, but the north of Europe is a big wind farm, and the south of Europe is a big sun farm. When I say south of Europe, it's including North Africa. So, and what is quite nice that when it's windy in the north in winter, the sun is less in Africa, but when it is summertime, it's the opposite. North Africa produces a lot, and therefore the two are totally out of phase, which is quite nice. So I guess Europe will import hydrogen, and I guess countries like Morocco and Tunisia have a lot to offer them. I guess you don't disagree with that, no? No? Yeah, now, if I look at mixing hydrogen and methane in the same pipeline, it depends on the quality of the steel of the pipeline. In Switzerland, we can mix up to 6% hydrogen in methane. In some countries, where the pipes are a bit newer, up to 30%. And Linde, for example, has already made a demonstrator where you can separate hydrogen from methane when the mixture arrives. So, for example, if you produce hydrogen in Morocco, you can mix it with some methane all the way to Gibraltar. When it arrives at Switzerland, separate the methane from the hydrogen. So that is not a problem. Now, some people are looking big. They can see further than just North Africa. The Germans are investing a lot in Namibia, in Chile, and so on. And as you can see, I guess people speaking about Power-to-X in Marrakech speak about this type of roadmap, where will be the big fluxes of energy in the 21st century, knowing that in the 20th century it was the oil tankers that were doing most of the flux, how energy will be transported in the 21st century. And in Europe, they have what they call the hydrogen corridor. And as you can see, the corridor B could be linked to Morocco quite easily. Now, if I look at what the EU plans are for hydrogen refueling station for trucks, they speak about one station every 150 kilometers. And basically, in urban region, they want the system to be able to deliver trucks at 350 bars and even cars at 700 bars. So basically, there is at the moment really political will in Europe to install a lot of service stations for hydrogen. There are also a political will to put service stations for electric cars with, as you can see here on the left, 300 kilowatt and even 600 kilowatt. So the Porsche Taycan is already 350 kilowatt charge. That's a lot of kilowatts, yeah, for one car. So they want a charger at 600 kilowatt. And for the truck, they are even thinking of having a charger at 3.5 megawatt per truck. That's a lot of energy, okay? But the European politicians are very ambitious. So it's for the scientists to do the job because that's what the goals of the in Europe, there are two ways to do a nitrogen station. Either you do like the Swiss, they produce hydrogen, for example, at a dam in the central part. They transport by truck the hydrogen to the service station where it is stored and delivered. The French do the opposite route. They transport electricity to the service station. They electrolyze directly at the service station. They store and they distribute. So that's the two business model. It depends if you have a good grid or a bad grid, and it depends if you have to pay a tax for the electricity or not. Now I have the pleasure for the last 5 years to be a scientific advisor of this company, GreenGT. And this year we were in Le Mans, and we set up a record at 290 km per hour on the ligne droite des Lunetières. And just to show this photo to say that hydrogen technology for car is there. It's quite reliable. We were expecting to do 300 km per hour, but the road was a bit wet and the air was humid. And in a fuel cell, you need oxygen from the air, but if there is humidity, you put less oxygen. And as we had seen before, oxygen is a slow one. So if you don't put enough oxygen in the car, it goes not as fast as it should. So next year, Le Mans 300 km, I pledge a beer to anybody in the room who's ready to take or beer or whatever you want, orange juice. Anyway, just to show here, it's written very small, but just to say that here the car has 2 electric motors, so the wheel can spin at different speed. But here we have 4 fuel cells, but with 1 balance of plant, and that's really the idea there. So 4 times 80, and with 1 supply of hydrogen and 1 supply of oxygen for the 4 system. We like to say that our fuel cells are the Rolex of the fuel cell because they are made by hands. They are really a nice piece of engineering. Those in the car have never been changed. and they work like on the first day. So again, you get well after your equipment as well. And just maybe the battery is 300 kilowatt with 3 kilowatt hour. So we charge and discharge the battery in less than 10 seconds because the battery is just there for braking and for accelerating. Because a racing driver is a bit binary, of full speed on or full brake on, and that's what the system is about. Of course, we don't do that to do racing car, we do that to do real trucks. So all the technology that we develop for the racing car, you should see the racing car as a fun, let's say, test bench to test your fuel cell, because there is a lot of vibration, a lot of constraint on in a racing car, so it's a very good test bench. And here, this truck is using two fuel cells, but with independent balance of plants for resilience. So it's twice 80 kilowatt, but totally independent. Okay, so one can work, the other one can be switched off, and so on. Here, the battery is much bigger because a system like this one, especially when you start the truck uphill, you need a lot of power for starting. So you need a much bigger battery. And of course, in Switzerland, we don't want to do trucks or cars because we're a small country and we cannot afford to have a big industry. So we made a partnership with a French company, Illico, that will produce those trucks in Switzerland. Now, we will not say too much about liquid hydrogen, just to say that many people are dealing with liquid hydrogen. This is Mercedes, where the advantage of liquid hydrogen is that you fill it like diesel, it takes 3 minutes to fill the tank. On top of that, nobody is going to steal your liquid hydrogen. It's not like diesel in France, where our truck drivers are always afraid that people will steal their diesel. Anyway, it has many advantages compared to gas hydrogen for storage on the truck. If you don't mind, I would like to switch to a bit of physical chemistry because some people are working on vanadium here in the room. Who's working on vanadium? So just for you, okay? So the others can sleep, it's just for you. I used to have a demonstrator in my lab where we had a Redox flow battery, 200 kilowatt, 400 kilowatt hour, vanadium. There we had developed some power electronics to do what in 2014 was a fast charge, 80 kilowatt, now it's a normal charge. And then we were driving an electrolyzer, Alkaline electrolyzer, but we developed this technology of dual circuit here to do hydrogen directly from a Redox flow battery. That's what I would like to present now to you. So briefly, this is a vanadium, a normal vanadium Redox flow battery. On the right, the electrolyte V2, V3. On the left, the V2, V3. On the right, the V4, V5. When you charge, you do V2 and V5. When you discharge, you do V3 and V4. Everything is in sulfuric acid. And I remind you, what is the beauty of a Redox flow battery? The power is the size of the electrodes, and the energy is the size of the tank. So you can have big power by having a lot of electrodes and small energy if you have small tanks, or small power if you have small electrode and big tanks, you have big energy. Whereas if you have, for example, the lithium phosphate, iron phosphate battery, because you store within the thickness of the layer, power and energy are totally related. Okay? You can try to make the film a bit thicker to make it more energy, but there are a limit to it. There is a limit to that. Now, what we've done in my lab is to add to the positive side manganese salt. So I understand that in Morocco you have a lot of vanadium from OCP, you have a lot of manganese from the ground. So here you can do vanadium 2,3 on the left and manganese 2,3 on the right. The idea is I will show you that if we pass the vanadium 2 solution on a catalyst, we will do hydrogen. If we pass the manganese solution on the right on a catalyst, we will do oxygen. And more important, we'll produce protons to equilibrate the pH of the full system. Okay. So are you ready for a little bit of electrochemistry? So this is water electrolysis. On the left, if I go negative, I do hydrogen. On the right, if I do positive, I do oxygen. Thermodynamic potential 123 volt, but because of the kinetics, it's spread. Now, because of the kinetics, it's spread. Now, if I use vanadium 2, we see that vanadium 2 is more negative than proton. So vanadium 2 should be able to reduce the proton. It's like when you put a piece of zinc in an acid, you form hydrogen and zinc 2+. Here is the same thing. The vanadium 2+ becomes 3+, and you do hydrogen. Okay. On the right, unfortunately, vanadium 4,5 is not strong enough an oxidant to oxidize water. That's why we use manganese. Manganese has a redox potential of 1.5 volt, and then it can oxidize water. Now, usually, manganese in solution dismutate to form MnO2, and it's a nightmare. But for some reason, which I cannot really explain because I don't know why, when we mix vanadium salt and the manganese salt, we don't have MnO2 precipitation. Now, that will be 3 slides of pure physical chemistry. There is an exam at the end. Okay. We're all familiar with the Fermi level of the electron in solution in the metal. Okay. So if I extract the electron from the Fermi level, I've got the work function. Do you agree with that? Okay. And the Fermi statistics is from the bottom. So we stack all the electrons in the metal until the Fermi level. Okay. So for the Fermi level in solution, it's a bit different because it's a Fermi statistic with 2 states, oxidize or reduce. Only 2 states. Okay. And when you have a 2-state thermodynamic statistics, the Fermi level is in the middle. As simple as that. Okay. And how do I define the Fermi level of these 2-state statistics versus vacuum? I just say it's the work to bring an electron from vacuum to this redox couple, i.e. to its Fermi level, and that will define, so to speak, my redox potential. So for an electrochemist, we speak about redox potential. If I want to speak to a physicist who think in terms of energy level, I will call my redox potential the Fermi level of the electron. Okay? It's a real Fermi level. It's a 2-state statistics linked to vacuum. Okay? So in electrocatalysis, what you have here is that you have a Fermi level in solution, a Fermi level in the metal. But if the reaction at the surface is slow, you put a particle, and the Fermi level on the particle equilibrates with the Fermi level of the metal, because metal-metal contact the Fermi level equilibrate. That was what we call electrocatalysis. You agree with that? Okay. Now, what I call redox electrocatalysis is different. I've got 2 redox couples, for example, they exchange different number of electrons. They don't speak to each other. Like vanadium 2 and proton don't speak to each other. But if I put, for example, a piece of gold or whatever metal in between, platinum, then the electron can go from vanadium 2 to the platinum or the gold, and then from the gold to the proton. And that is redox is a redox reaction. 2 redox couples want to react, but by putting the metal in between, we allow the reaction to take place. Okay. Now, of course, if one reaction is fast and the other is slow, for example, if the one at the bottom is going right is fast, but the Fermi level on the gold, for example, will equilibrate with the Fermi level of the redox on the right. If it's the first reaction which is fast, the Fermi level equilibrates with the one on the left. Okay, so that's the principle of electrocatalysis. Now you will tell me, how do I change the Fermi level of a particle in solution? Well, that's very easy from electrostatics. It's just the charge. If you take, for example, a piece of gold in there, it has a Fermi level given by gold, 5.3 volt work function. Now, if I charge my gold positive, it will be more difficult to extract the electron. If I charge the gold negative, it will be more easy to extract an electron. Okay, so the nanoparticles, the Fermi level, so to speak, of the voltage of the particle, if you want to speak as an electrochemist, will change simply by changing its charge, because there is no wires. Electrons cannot appear from a wire. So the redox couple will give the electrons, the charge will adjust in such a way that I can do redox catalysis, electrocatalysis. And that's what we do here for the vanadium. I'm going to use molybdenum carbide. Here on the top here is the redox potential of V2, V3. On the left, the one of the electron. Oops, sorry. And then here, the V2, V3 is a slow reaction because it's heavily hydrated on molybdenum carbide. But hydrogen is much faster, which means that I do hydrogen at the speed of arrival of different to the particles. Okay. So if I want to cheat a little bit the system, what I will do, I will put few particles of MO2C where I do the hydrogen evolution, but a large area for the V2, V3 to occur. For example, I can take a long carbon nanotube and put, let's say, 2 nanoparticles of catalyst. The vanadium has plenty of surface area to react, okay, to be oxidized, and then the electron goes and on the particles and evolve hydrogen. Okay. The same on the right for manganese 3 and 2. And just to show you how it works when you put, so on the left there is a ball of ceramics covered with molybdenum carbide. Okay, you put a ball of molybdenum carbide solution and you got hydrogen evolution. Okay, and to make a reactor is easy. It's just a polypropylene reactor, 10 bars maximum because it's plastic. And so for the price of charging a vanadium battery, you do hydrogen for free. You like it? Just for you, I said. So what we have been proposing to set up as a company is to say, okay, Switzerland has no energy. The only thing we will have is solar panel on the roof. Okay? And because the sun is only at lunchtime, we have to store energy. So we will need to have plenty of distributed energy storage capacity. And Redox battery are good to do distributed energy storage. It's the size of a container. So basically, the idea there is to have an intelligent vanadium manganese battery that feeds from the grid or your solar panels. When you want to do the fast DC charging of your car or your truck, then you charge either from the grid, but you can use the battery as a boost, because when you've got a truck arriving with a few hundred kilowatts, then it's a bit of strain on the grid, so the battery can do the spike, okay? And then if you want to put a car with hydrogen, well, you just discharge chemically your system through the catalytic reactor and you do hydrogen. So that's what we try to set up as a business model for what we call an energy station, because the idea there is to say, okay, if we have electricity cut, and in Europe now we are thinking in business model, what happens when the electricity is cut, okay? 21st century Switzerland, okay? People are worried about their data center, people are worried about their fridges. So if you are a Carrefour market, if your fridge goes down, if your data center goes down, there is no more Carrefour market. You agree? So those guys, they will need energy stations for storing electricity, maybe to have electricity for their truck, hydrogen for their truck, and things like that. Okay, and now for something only for UNESH. In the previous slide, we did a lot of printing, thin film, photonic curing of inkjet printed material. And if you take, for example, you print silver ink, nanoparticles of silver, they melt at 800 degrees. If they are, for example, on a polymer, I flash with the xenon lamp. And the xenon lamp is the flash that photographer had at the beginning of the 20th century. It's just a glass tube filled with xenon, and they discharge a lamp, the capacitor, okay? 100 years old technology. As you can see here, the silver absorbs the light energy enough to melt the silver. So it means that the silver will go to 800 degrees, non-equilibrium, for a few microseconds or milliseconds. Okay? That's well known in the printing industry, but we are speaking about 20 kilowatt per centimeter square. Okay? That's a lot of energy. So briefly, in my lab, we used to do sensors. So there it's quite easy. We print the carbon, we flash its Q. We print the silver, we flash, we have metallic silver. We print the silver chloride, we dry it. And so print, cure, we can do a sensor which is multi-layer in few steps rather than taking the thing out, going to the oven, put it back on the printer and so on. Anyway, and we say, okay, maybe we can do some chemistry with that. If I take sodium, nickel chloride or iron chloride, and I print it, I will reduce the salt to nickel iron particles, and I will oxidize the solvent, let's say ethanol, for example. And for example, to do the molybdenum carbide I had shown you before, here we use molybdenum oxide, we flash on the graphene, and we form directly molybdenum carbide. So we can do carbide directly on carbon. So we decided to do something for what we call banana split by Photo-Pyrolysis. The idea was to have a reactor which is a bit like my watch here. So steel with glass on top, okay? Because that to be on the printer at the beginning. So we put inside some dry banana skin, we flash a few milliseconds, and what we have is hydrogen and biochar, okay? Bit of CO. So basically, we could split biomass in few microseconds or milliseconds and obtain this biochar there. And that's what we call photopyrolysis. What is pyrolysis? Pyrolysis is how to bring and to break molecule, okay, with kinetic energy. So fast kinetic energy because of temperature, the atom goes and we start a chain radical reaction. Okay? In photolysis, a photon is absorbed by the chemical bond and the electron is ejected. Okay? And we believe that photopyrolysis is a mixture of the two processes. Because as chemists, we know very little how to break a molecule. So as a physical chemist, I know that if I've got my atomic molecule, I put some photon in it, I will have vibrational energy until it breaks. Okay? But as soon as I've got 3, 4, 5 atoms, I don't know the distribution of energy in the different vibrational states, and therefore we know very little how to break molecules. It's crazy, huh? We know how to burn molecule, we know how to make molecule, we don't know how to destroy molecule. If you think of it, and if you look at the literature, it's very interesting that even the transition state theory does not apply to molecular dissociation for polyatomic molecule. So if some people want the Nobel Prize in the room, there is a real problem of chemistry, how to break a molecule. Anyway, so if we look at the hydrogen content, you guys are doing cellulose. In cellulose, I've got 6% in mass of hydrogen. In water, I've got only 11% in mass. So I've got twice as much hydrogen in water than in cellulose. Not too bad. You have more hydrogen in a liter of petrol 95 than in a liter of water. Okay? So the question is, are we obliged to do hydrogen only from water? And the point I tried to say is that no, I think if we look at the biomass, so even the base would be methane. Methane cracking is the holy grail. If you break methane, you carbon zero and hydrogen, you are the king of the planet then, because you solve all the world problems. Okay? And that people do that by plasma. Anyway, so what we used to do for the banana is just this recipe. But just to say that if all the banana skin of the world were photopyrolyzed, that would be equivalent to 300 megawatt of electricity. Okay? Just is to say there is a lot of hydrogen there. Now, if I don't want to be honest, I would say, look at that. I've got a lot of hydrogen, a bit of CO, a bit of methane when I do a chromatogram. Of course, it's a TCT detector, so the small mass has a big peak. In fact, I've got as much CO than hydrogen, but the detector is much more sensitive for hydrogen. So because we are chemists, I'm not going to lie to you. If we were banking people or business people, I would tell you, hey, look at all the hydrogen we can do. Anyway, let me say this. The interesting thing here is that we can do very porous carbon, which is conducting, and the system does not depend on the substrate, glassy carbon, platinum, or glass, or whatever. It is really the banana that is exploding. So we start from the banana, which is just lignin and cellulose. It explodes from carbon and gases. Okay, that's where the carbon goes. The hydrogen is 66% of the hydrogen. The carbon, 66% goes as a biochar. The oxygen from the cellulose goes mainly into oxygen gas, a bit of CO and very little CO2. Okay. So we've been playing with that with the dry part of the biomass, for example, terreau in French. So when the bacteria have done their job of digesting the biomass, you get a solid part that can be photopyrolyzed. Coffee grounds for Nestle works very well. Tires is very nice. It's just carbon and hydrogen. So if you photopyrolyze rubber, you only get hydrogen, pure. Okay, the brain don't get pure carbon because the tire is full of rubbish, zinc oxide, silicate. There is a lot of inorganic fillers in carbon. And we even done it on the tar from the road, because in Switzerland, some of the tar is full of toxic compounds, and it is sent to Holland, where it's pyrolyzed in oven, and then the dry part is put in an oven. Anyway, so that is to say, pyrolysis is one of the oldest chemical techniques of the world. The Egyptians used to do tar. So just take wood, you put clay around, you put the fire at the beginning inside, there is no oxygen, and you get charcoal. Okay, people have been doing that for a long, long time. Okay, and the Egyptians, they were recovering the tar to make the boat waterproof. So the charcoal, I don't know what they did with it, cooking, I guess. And then people realized that when you do holes in it, in the 18th century, when all this Priestley, Lavoisier of this world started to realize that the gas is a molecule, they realized that if they make a hole on the top, sometimes it took fires, there was hydrogen. If they put a cold metal plate, they would form water. And that's why they call it this gas hydrogen, the gas that forms water. Okay? So very old process pyrolysis. And that is for you, Guinel. These guys here, Levidian, they take methane and they say that they use a plasma to ionize the methane, and they even say that they direct microwave at it. So I can understand it's a microwave plasma system doing only hydrogen and graphene. And for me, this is the holy grail of what we need. We start from methane. We have negative carbon capture with graphene. Maybe one day we will do carbon nanotube, God knows what. Okay. But and if you look at Graphos in Germany, they do the same thing here. They call it plasmalysis. And what is the very interesting part of plasmalysis compared to electrolysis is that you need 1/3 of the energy. So if you have renewable electricity and you do plasmalysis, you need only 1/3 of the electricity you need to do electrolysis. You guys are good at this.
Very interesting, huh?
Yeah?
Oh, very important.
I think it's very important. The problem, science is done in silos. So the physicists are doing the graphene, the chemists are trying to do electrolysis. People don't speak often to each other. But here, for me, if I was 20 again, so if I was your age,
Young.
no, it's outing everywhere. If I was young, I would move in this direction. Because if you can do carbon, then afterwards, as chemists, we know what to do chemical reaction. We know how to functionalize carbon. So we open to. And if I take, for example, Inoka in France, they do wood, but they do normal thermal pyrolysis. They do steam reforming behind, and they do hydrogen for electroshock. There is this company, BioGrid. They do like Photo-Pyrolysis, but it's just electric pyrolysis. And again, they do hydrogen, CO, and carbon. So they do the same thing that we do by photo, but just by heating in an oven, which is very nice. Okay, that is to say, pyrolysis has a lot to offer. And I will stop here. Thank you very much for your attention.
Thank you very much, Professor Giraud, for this very inspiring, very broad also presentation, touched on the many subjects. So what I would like to do now is I would like to ask my colleagues Laura to join us over there. So we will have a discussion. We might like to sit down. Thank you. It's very fantastic. So we'd like to have a discussion with you. I will have the experts also contribute to this discussion. Maybe we'll start with Laura.
Yeah, sure.
And then towards the end of this discussion, I will also ask the public if they have any questions for you.
Hello. Thank you very much, Professor Arami, for giving this opportunity to act as a panelist. My first question about to Professor Giraud about how do you think that Morocco as a country can incorporate hydrogen energy in future for its energy transition market?
As we said, Morocco has an ideal geographic situation for the capacity factor of renewable energy. So if you invest in a solar plant or a windmill in Morocco, you will get more energy than if you put the same equipment in north of Europe. As simple as that. Okay. So now the question is, what do you do with your renewable electricity that cannot travel long distance? And I believe that in this world, this crazy world where we are at the moment, there is such a need for fertilizer. There is a food crisis worldwide. So if Morocco is already independent in fertilizer, for your agriculture, it's a major advantage. Now, another point we didn't have the time to discuss, of course, is green steel. If you look at the steel industry of the 20th century, it was based where you had coal and iron ore. Now you can see in the north of Scandinavia, where they have hydroelectricity, hydrogen, and iron ore, doing green steel in Sweden. Okay. Now I'm ready to bet, I don't know what, that in 20 years, the west coast of, let's call it South Sahara or west coast, or this part of Morocco, that anyway, near Darla, you have the wind, the sun, and the iron ore from Mauritania. I think it doesn't take much to bet that Darla, like the region, has all the potential to become a big steel center in the world. And if you look at a place like Fos-sur-Mer in France, they will disappear. ArcelorMittal, if you think at Fos-sur-Mer with ArcelorMittal in France, it's crazy. You import the iron ore by boat. You import the coal by boat. You make the steel in south of France. It has no future. It will never compete with if you do it here as a green steel.
Thank you very much. It's really indeed a quite good explanation. Now, my next question will be what will be the Morocco's role in future green energy production and its transportation to Europe and Switzerland as well? So how do you foresee this future?
Well, the key question, okay, hydrogen is a vector. How do you transport hydrogen? By pipe, that's the easy part. Liquefied, that's a bit more complicated, but it's feasible. Then you've got liquid hydrogen carriers. Afterwards, it's a matter of belief. Do you believe that it's easier to transport ammonia, which is toxic, than to transport hydrogen? Afterwards, it's a business consideration, which is not my strong point. Is that easier to make methanol and transport methanol? Afterwards, it's money, okay? So there are chemistry, and then afterwards, it's a matter of money, which are the best route to export. Is it to export by sea? Is it to export by land? And of course, it's not only exporting to Europe, don't forget export to Africa. You guys have a huge market. If you look at the population of Europe is going down, the population of Africa is going up. Where are your customers tomorrow? Are your customers in Europe or in Africa? For you to decide.
Yeah. So in relation to the question, so how do you think the techno-economic analysis of the transporting hydrogen? So how will be the cost and what could be the impact on the end users? For instance, hydrogen-based fuel cell vehicles.
I'm not qualified to speak about cost, and cost today is so unpredictable with what's going on that I would not answer this question because I can't and because I think it's impossible to answer.
Yeah.
We live in a completely schizophrenic life. We continue our life like if nothing happened, knowing there is a war going on that could go wrong anytime, or even more wrong anytime. Yeah. I don't know how you are when you wake up in the morning, but some morning I switch on the news, I say, oh no, what kind of a world are we?
Yeah, my next question will be, how do you view the competitiveness of electrolyzer technology in terms of electrocatalysis design or membrane designs? So how this cost of hydrogen will be interrelated to these two topics, electrocatalysis or membrane design?
It will be membrane.
Yeah.
That's where all the effort is, and that's where the saving can be done. The price of electrocatalysis is noble metal. What is the price of platinum? Most of it is made in Russia and South Africa. What is the price of iridium? Most of it is from South Africa and Russia.
I want to go back to the last question.
Yes.
So, what choice do we have, really? Can we keep? We can only pretend that there is nothing wrong with the world. That's the only thing we can do. Because I think if we start thinking about all the problems,
that's why we always we all go on like if everything is normal until we see a buyer. For example, if I take the car production or truck production, now we wait for parts for 1 month, 2 months. Parts that you had online in 24 hours, now you wait for 1 month. I don't know if it's the same here in Morocco, but in the lab, even for steel in Europe, you cannot buy steel. or a switch lock to connect a hydrogen bottle to your lab, you wait 1 month.
Okay, so that's.
Yeah, thank you very much.
Thank you so much for answering the comments.
Thank you, Professor. Really important interesting presentation. If I understand, today your use depends on Russia in gas, and tomorrow it will depend on Morocco to use hydrogen, green hydrogen, because according to your presentation, will be one of the big players maybe in the future in producing hydrogen, green hydrogen.
With Tunisia, with Namibia,
North Africa.
North Africa.
Yeah.
And we could even hope that one day Libya is normal enough to be a player as well. Algeria also.
Yeah.
But, and something, we speak about hydrogen, but perhaps there is more money to be made to store CO2, because the Swiss are going to continue burning things, okay? They don't know what to do with the CO2. The only thing they have is money.
Yes.
Well, I should not say that. So they want to evacuate the CO2, as we say in French, loin des yeux, loin du cœur. So if the CO2 is, we sell it to Morocco to put on the ground, they will feel good.
Yeah.
And they will pay for it. So it's already 70 euros a ton at the moment. The CO2 certificate.
Yeah.
And you need 0.7 megawatt hour to produce it.
If we stay in this beautiful scenario that Morocco will be a big player, a big producer of green hydrogen, maybe we for sure will need to balance between production, consumption, and we will need several methods to store this hydrogen. And one of the methods you have said maybe good for Morocco to use mines of salt dome.
Salt dome, like
Yeah.
Can you examine it?
Can you
So, well, it's a geological formation where you have salt covered by as a dome. The other way to do it is to pump water inside the salt, pump the salty water, and you end up with a cavity. And that is established technology for methane. People said that in Texas they want to do it at 200 bars hydrogen under the ground. And of course, the beauty is seasonal storage. We don't know in Europe how to store hydrogen from summer to winter. Okay. So if anybody can do seasonal storage, salt mine, and only the Germans and Morocco, to my mind, in Europe are the best place to do it, then it's a winner.
Yeah.
Because
we don't need energy to store. Just
you need to compress
with the gas.
Yeah. You need to compress and then it goes out afterwards. So
and water.
So
we need water? No, nothing. Okay, good, good. And Professor, also you gave an example to how to store electrochemically the CO2. It's some kind of battery. We can use also this system to deliver energy. No?
Well, officially yes, but it's not very efficient. But it's a very good way to do direct air capture, because everybody says CO2 capture. Where do you want to capture the CO2? So if you capture in air, it's clean. Now we breathe it, 400 ppm of CO2 in the air. It's and for electrochemistry, it's fine because we just polarize the density. Current density is not too strong. It's easy electrochemistry. Now, if you want, people say, oh, why don't we collect CO2 directly where we form it in the chimney? But this CO2 is dirty. Contain a lot of H2S and so on particles, and then if you put that into your electrochemical system, you kill it. Okay, it's much easier to capture clean CO2 from air than to capture dirty CO2 from a process.
So, okay, can I have a lot, so I can continue. Yeah. Professor, you gave 2 examples of electrolysis using polymer electrolyte membrane. Alkaline electrolysis. If we want to compare between the both devices, which is the best technology?
At the moment, of course, there is also solid oxide fuel cell, solid oxide electrolyzer, which are coming, but they are not yet at the industrial level. So there will be more systems coming, like high temperature electrolysis, solid oxide electrolysis, I think there is still room for research. Now here you have two systems, alkaline and polymer electrolyte membrane. They are commercially available. As I say, one is more chemical factory, but it can go to megawatt, gigawatt easily. The PEM will go apparently to tens of megawatt, perhaps hundreds of megawatt. Can it goes to gigawatt? Yeah, gigawatt is a lot of meter square of electron. And so if we take the lesson of the chlorine industry, they have won something like 100 millivolts over 20 years just by improving the catalyst by catalyst, very incremental research. And as I said, I think the most important afterwards is the operation. You have to make sure your system does not degrade. And if you don't want your system to degrade, you have to operate it properly. And you have to. So I believe an engineering school like this one or others, we have to train people to run this type of factory that do not exist today. And we don't want people to create new things because what we have is already quite good. Yeah, we can marginally improve it, but it will be incremental and difficult. But once you buy a system, make sure those things cost millions, yeah, if not more. So you have to operate them very carefully. Yeah. And of course, for the young people in the room, AI management of system is the future. Okay, so you need artificial intelligence to and that's something. It's a business which does not exist yet. So basically, plenty of sensors in all the factory, and after that, from all the data acquisition from the factory, defining model. It's like in the racing car I've shown you. The most important part is the computer. It's not the fuel cell. It's not fuel cell. It's just hardware. Kakayri. Okay. The important part is the management system, and of course there are sensors everywhere. And then afterwards is the program. A car of tomorrow will be a computer on wheel. Okay. And it's not the hardware is the same for everybody. It's the way you manage it and the way you understand your system which will make the difference.
Basically, a balance of plant.
Balance of plant, but with AI.
Yeah.
I was telling the battery at lunchtime, at the moment, my job at the car is to put microphone. Because with acoustic sensors, we learn how to listen to the car. Yeah. It sounds stupid, but just with microphone, when something starts to go wrong, we have a leak, it starts to make ultrasound. The microphone can detect the ultrasound before we realize we have a leak. Okay, and so on and so on. So I think the engineers of tomorrow will spend more time in front of their computer. It will be data acquisition, data storage, data acquisition, data analysis. The hardware part, I'm sorry to say, but we are the chemists, but at the end of the day, the chemists, we are not so important as such. It's the management which is important. That's true.
I have also a question. But you say that it's easier to connect polymer electrolyzer based membrane electrolyzer to PEM than alkaline.
No, I just said that. I said that a PEM has no chemistry, so you can put it in, for example, in this building, you put a PEM downstairs, you don't need a chemical engineer to maintain it. You install an alkaline electrolyzer in this building, you need somebody who comes every day to verify the pump, to verify this, to verify that. It's a chemical plant. Okay, that's the only thing I said.
Yeah. But for those you need a converter and so on. Yeah.
So let's open for the public if you have any questions. Otherwise, we'll get back to you.
Thank you for this very nice inspiring talk. So I have two questions. General question. My first question is about fuel cells vehicles. Please comment on the competitions of this fuel cell technology against lithium-ion and sodium-ion batteries in EV. And my second question is also if you could comment on the conversion of CO2. Recently, we see the producing polymers from the CO2 conversion. So, but if we can produce some plastics from this, if it's useful, if it's good solution, alternative solution to storing it underground. So, thank you.
So the first question is battery versus fuel cell. Yeah. In terms of mobility, it is clear that if you have an electric car, and I've got an electric car, I use battery because you recover 90% of your energy, okay? 95% of your energy. Don't forget a fuel cell has a yield of 50%. So when you have a fuel cell car, 50% goes to it. Now in Morocco, it's bad, but in Switzerland it's not too bad. I had a hydrogen car. At least I was warm in winter. Because in your electric car, sometimes you're afraid to put the heat pump. So you have drivers driving with body and gloves because they are afraid to lose some energy for their cars. The fuel cell keeps the drivers warm in winter. No, but the fuel cell you lose is not an efficient system. So the fuel cell you do it if you cannot use battery. Like for a truck, if you have a truck that you need 5 tons of battery, it's a bit useless in a way. So a fuel cell is very cheap to do. It's just a bit of graphite if it's a graphite fuel cell, or latol, just a piece of steel, a piece of membrane. So the hardware of the fuel cell is trivial. Okay? What is expensive is the reservoir for the gas because of safety. But the battery have made so much progress. When you see the Tesla now, the 1 million mile battery by using very small powder, you will change the driver before you change the battery, because I don't know many people who will drive 1 million miles in their lifetime. I think it's more driver recycling that we should worry about than battery recycling. And the second part was about it's the Holy Grail, of course. That's where the organic chemist. I didn't show you slides today, but I can oxidize water with 1 organic molecule that's stacked to do 4 electron and 4 proton reaction. Chemists make matter. Chemists are so important because we know how to transform molecule. Okay, so chemists can make our future. I've got nothing against people in material science, but in material science, you take a material, you purify it, you grind it, and you use it. Okay, so if I want to make a joke. But chemists have the possibility to transform matter. And that's the beauty of organic chemistry. That's the beauty of inorganic chemistry. You can make new materials. So if you can transform your CO2 into a polymer, well done. And people are working on it. And of course, we have to do research on that. And of course, it's the future. I mean, every funding agency at the moment put a lot of money on CO2 chemistry, and rightly so, I would say.
I have a question since we're talking about storage. Solid storage of hydrogen. You have not talked about it. Is there a reason for that?
You want me to go on to
talking about hydrogen?
Yeah, well, you know the brand with hydride. Hydride, people have said they have a lot of future for us. Since I am a student, I listen. Hydride have a lot of future. Maybe in 50 years, they will still have a lot of future. The problem with hydride, it works extremely well in your glove box if there is no oxygen. Okay, as soon as you've got oxygen, it reacts with the hydrogen to do water, which means corrosion of your hydride, corrosion of your material, and basically your tank becomes a pot rouille. So corrosion of hydride is the beautiful things in the glove box.
So what do you think the potential future of this technology?
Well, if I had to invest my own money, I would not invest it there.
Ja, want dat van porous material storage eigenlijk.
I know, but porous material is different. Zeolite, moss and so on around the future. But you asked me about hydride.
Well, thank you, Professor, for the nice presentation with this information knowledge. I want to talk about the VPR3 type perovskite materials.
About this?
Perovskite sites.
Perovskite.
As a processing materials for water supply and as coupled for soil cycle seeds. You have an idea.
I would say I'm not a specialist on perovskite. Now, of course, it's a material worth investigating. That's the only thing I would say. But I'm not a big fan of perovskite for solar panels because they are based on lead, and lead is not a nice metal. But for what you said, for water splitting, yes, why not? Let's investigate. It's a family of materials that we should not ignore. I think no.
So thank you, sir, for this informative presentation. So, sir, I have one question about hydrogen transport. So my question is, what is the best way to transport hydrogen? Is it better to transport it as a liquid hydrogen or ammonia or a pressed hydrogen?
So if you take Texas or the north of Europe, Air Liquide, for example, operate a big pipe network in the north of Europe because hydrogen goes to all the refineries of Rotterdam, up to Hamburg, up to the Ruhrgebiet, and so on. So pipelines of hydrogen is the simplest. Okay, for very long distance afterwards, it's a matter of cost, of course. Liquid hydrogen can be transported by train in containers. So if I take the case of Switzerland, we import from Hamburg a train of petrol and diesel every day. That's what the consumption of the country. Why not importing from Hamburg, where there is all the North Sea hydrogen production, a train of liquid hydrogen to Switzerland? Okay. For example, the beauty of liquid hydrogen for filling a truck, like I've shown you, is that you don't keep it cold. It means you put in your truck just what you need for the trip. So you have a tank like that made of titanium. Okay, you put a bit of thermal isolation, and what you have to do is just to control the boil off of your liquid reservoir in such a way that the boil off corresponds to the consumption of your truck. Okay, you have a buffer of time just to buffer, and of course you cannot keep it for the next day because you cannot stop the boil off. Okay, so you make sure that at the end
The train is
the tank is very light. I mean, I've seen, for example, a liquid hydrogen drone at the last hydrogen meeting in Paris from a helium company in Korea. The tank is 2 kilos. So, and then it's enough for the drone to fly. Okay, when there is no liquid hydrogen, the drone has to land. And it's the same, for example, the philosophy of Airbus when they want to develop a hydrogen plane. They put just liquid hydrogen enough for takeoff. So you fill the tank for doing the takeoff part. Once the plane is in the air and far away from city and pollution, they switch back to kerosene to fuel. Again, they don't need big tanks for that. It's just a metal tank because you use the boil off. You want hydrogen to evaporate. Now, liquid hydrogen carriers, as I said, is a matter of cost and philosophy. Ammonia is a matter of, do you want to transport a toxic material or not? Afterwards, ammonia can be burnt into a combustion car, for example, but you will form NOx. What is the situation with NOx? Afterwards, I am agnostic. If this technology is good, why not? I mean, I don't favor one technology compared to another. I think everything is worth considering. You have to make the business model for it. If it makes sense economically to do it, let's do it. I've got nothing wrong. Same for methanol.
We have a question online.
Question from the online audience. It says, "Hello, sir. Thank you for such a rich presentation. I have a question regarding comparing the methods for hydrogen production and photocatalysis. What is your input about the subject, efficiency-wise, cost, scalability, and ease of implementation?"
Photocatalysis needs a lot of square meters. Okay? So if you look at any paper who compare doing hydrogen directly on electrode or using a solar panel and a small electrolyzer at the side, there is no photo. The cost per meter square of photocatalysis is such that at the moment, photocatalysis is a beautiful playground for physical chemists. We all love it. I've got some colleagues at EPFL who published plenty of papers about that. At the moment, the economy is not yet there. So a solar panel is so cheap, an electrolyzer is so cheap. Do you want to have kilometer square of electrode with electrolyte on it? Don't forget, a solar panel is a rock, it's a stone. And they have to survive 30 years in the sun.
Okay. Do we still have some questions?
A question of efficiency.
Maybe, Professor, what we could mean by efficiency? It is the efficiency between input energy and output energy, or the amount of hydrogen converted to water converted to hydrogen when we speak about electrolysis.
It's what you pay. So usually you pay the electricity, you don't pay too much for the water. So it's really how much kilowatt you put in and how much kilos of hydrogen you get out.
Okay.
To desalinalize water is quite cheap in comparison with the price of electricity. So, and water, seawater is free. So.
Thanks, Professor, for your nice presentation. It's inspiring presentation. So, first question is related to the future of porous materials such as mold with organic framework for the transportation of hydrogen. And second question is related to the green production of hydrogen from water. So, do you think that this production will not cause any threat to our water security?
So regarding MOF, MOF has been the revolution in organic chemistry of the last 20 years. It's a fantastic way to self-assemble molecule to do. There is so many things we can do with MOF. So MOF engineering as a chemist is a super playground and storing, you can store whatever you want with MOF, from CO2 to hydrogen, and functional MOF, flexible MOF, even. So yes, I think, as I said before, chemists have a lot of things to do in the energy transition because they create things, and MOF is something you create. So yes, we should study that. And then afterwards, are we going to run out of water if we do green hydrogen? Of course, you don't want to compete with drinking water. That's why you have to do it by the coast where the water is free. But it's like in Germany doing biofuel with corn. You know, do you think it's clever to make diesel out of food?
Okay.
What about this? What about electrolysis of seawater instead of drinking water? Is it something that we could consider?
Plenty of people have tried. It's too complex a matrix. Already to electrolyze KOH and keep it clean is difficult. To electrolyze water for PEM, you need very clean water. It's much easier to do reverse osmosis. Reverse osmosis has become so cheap now that making electrolysis of seawater, we discussed that at lunchtime, everything will deposit on your cathode, the calcium, name an element. Seawater is so full of metals and this, even if you have ppm of it, you know, if you electrolyze for hours and hours and hours, at the end of the day, you end up with all the periodic table on your cathode.
Yeah.
Deposited.
Yeah.
And on the right, you will do chlorine, so you will do hypochlorite, you will do eau-de-javel. You're going to sterilize the sea. I'm not sure the fishermen will be too happy if you put lots of eau-de-javel.
Yeah, correct. Yeah.
So difficult.
Okay. Great. Then I'd like to thank you so much, Professor Giraud, for this entertaining, very interesting talk and discussion. Big hand of applause. Thank you, our panelists, for
Thank you very much.
thank you. Animating this discussion, and everybody else. Thank you so much for being here with us today. And see you next month.
I would like to thank you and
ENSUS
say to
Discussions.
the young people in the room, you are the responsible for what will happen to the world. I don't think it's the job of your guys to do the energy transition. It's your job, it's your planet. And when my children say, we are going to inherit something bad, I say, look, I took the planet as it was, I tried to make it better, but it's your job to make it even better.
Yeah. Okay, thank you.
That's why they go for things like graphene, which is the shame technique.
But so that all, we don't really understand, that's why I asked about microwave, because you know, relative